Alright, EV statistics, we're ready to start Chapter 2 and 2.1, describing location in a distribution. So we're going to use two methods to describe that. We're going to talk about a data point's location in a distribution in terms of percentile. And we can look at that graphically by looking at an ogive, or a cumulative relative frequency graph. And then the other way we're going to look at it is we're going to look at a standardized value of a particular x value or a data point inside of a distribution and talk about how many standard deviations that particular data point is from the mean. Here are our objectives. We're also going to talk about what happens when we transform the data within our distribution. When we add some sort of constant, or when we multiply it by some sort of constant within this data set. How does that affect our mean? In other words, our measure of center, or our shape, and even our spread, our measures of spread, IQR, or standard deviation. Okay. So we can look at what percent of observations are less than it when we look at a different value within a distribution, right? So we can talk about a p percentile of a distribution, right? And what we're doing is we're saying, hey, this value is at the 84th percentile, say. What we're talking about is that 84% of the scores are below that particular score that we are talking about. All right, and we can look at this example, right? We talked about examples of test scores. And we looked at it in this way. We actually, in our example that we looked at, we wound up looking at it in the reverse way, but it still worked. Especially for the purpose of creating our ogive. Otherwise known as our cumulative relative frequency graph. And now, you guys know what this ogive is all about. In other words, you know how to interpret it. Right, so what we're saying is, if we were to look at this graph, we're saying that a person who was age 50 at inauguration was at the 20th percentile. Pretty awesome. Let me see something. Here we go. Now, we also were able to talk briefly about our standardized value. Right? In other words, what we're doing is we're measuring how far away, or how many standard deviations from the mean, a data point lies. Okay? So with this formula, we have z equals x, right? So that's our data point that we're wanting to know about, right? Minus our mean divided by standard deviation. And if we wanted to shorthand this, in this case, we could write that this is the same thing as x minus x bar divided by, and right now we're using s sub x as our standard deviation, right? So we could write it in this way as well. So we can interpret this. Jenny earned a score of 86 on her test. Right, the class mean was 80, standard deviation 6.07. We were able to get that because we have all of the class scores. And we'll discuss why that's relevant later. For now, it looks like she was around 1 standard deviation above the mean. All right, and just real quick before we move on to transforming. Um, as we go through the class, it's going to have a lot more relevance, right? Saying that something is about or approximately 1 standard deviation above the mean, we're actually going to know how much of the total data that encompasses and even find a percentile for that particular data point as we go on. For now, we just want to interpret a z-score or a standardized value in terms of what it tells us about the location of the data, of this particular data point, I should say. All right, what happens when we transform data, right? In other words, if we had to take some units of measurement and change them, right? Or if we had to add something to each of them, right? In the instance of maybe a curve, if we were to curve test scores just by adding them. Some teachers do that, right? They'll say the lowest or the highest test score was, I don't know, a 92. Some teachers will curve grades based on bringing that 92 up to 100%. In other words, everyone's grade is going to get kicked up 8%. And we'd be interested to know how that would change our measures of shape, center, and spread. All right, so what is going to happen? Well, it's going to add whatever constant, whatever number we've added to each data point. It's actually going to add or subtract that from our measures of center, but it's not going to change our measures of spread. So let's check that out. All right, so let's look at this one and see what happens. We look at the dot plot on the top. It says error underscore m. What we've got is our transformed data, right? And then underneath is our original. That's our guesses, right? So error was our guess minus 13. Let's look at the shape of the distribution. It hasn't changed at all. All that's happened is each data point has been shifted 13 units down, or 13 units in the negative direction. All right, and remember, right? We're looking at what has happened. What has happened to our socks? What happened to our socks? Well, it looks like the shape has stayed the same, right? Outliers, if they were outliers before, they're going to stay outliers after this transformation. What about our measures of center? Well, if we look at our measures of center, right, we've got a definite change. A change by how much? It's been decreased by 13, which makes sense. This right here, what is that? That's our standard deviation, isn't it? What happened to our standard deviation, right? Or our measure of spread, right? Our measure of spread, that has stayed exactly the same. Our other measure of spread, right, our IQR, has also remained the same. And then we also missed, what is this guy right here? It's our median. Has that changed? Yes, definitely, right? Our median has been decreased by 13 as well. Excellent. So we have our shape, outliers, center, and spread, our SOPs have been taken care of. And it appears that really the only thing that has changed was our measure of center, right? Measure of center. Our range also, right, turns out to be a measure of spread, but not one that we use very often. All right, something a little different happens when we transform data by using a scale factor. All right, so these transformations affect things much differently. So what I mean by a scale factor is we're going to multiply or divide, right? If we multiply, our scale factor is a whole number. If we're dividing, our scale factor is a fraction or a decimal or some number less than 1, or between 0 and 1, really. All right. If we're going to multiply by a constant, it's going to multiply or divide, right? I'm going to say multiply, and I'm going to assume that if we're dividing, we're talking about multiplying by a number between 0 and 1. That's a better way to look at it in this case. So when we multiply, we're going to see changes in our measure of center and our measures of location, percentiles. Essentially, our quartiles will change as well. And our measures of spread in this case are going to wind up changing, okay? The shape, however, is going to stay the same. Let's look at that. Okay. We've got a group of Australian students. They're having some difficulty with the metric system. It may not be helpful to tell them that their guesses tended to be about 2 or 3 meters too high. Let's convert the error data to feet before we report back to them. They are roughly 3.28 feet in a meter. It's for our Australian students. It's a good day for it. All right, let's look at it. So, they don't have a key. They haven't told us which is which. We got to figure it out, huh? So we got error meters and error feet. So I don't know why Australian students are having difficulty with the metric system. I believe they use the metric system in Australia because I know that Australian surfers are measured in kilograms. So, an interesting problem. All of that's neither here nor there. We just get down to the brass tacks of this thing and get it done. So it appears that our top graph is actually in meters, right? So that's the distribution that we began with. And then when we're converting to feet, we're going to multiply that by a factor of 3.28. So what are we seeing? Obviously, our number of data points n stays the same. Our mean, however, has been changed, right? By what? By a factor of 3.28. Right here. Where we see that that's been increased by a factor of 3.28. What else is happening? Well, it looks like our standard deviation also has been increased by the same factor. In fact, our range, IQR, all of our measures of spread have been changed by that same factor. But what about our median? The same thing has occurred with the median as well. And when we look at this, really the shape has not changed. Things just got a little bit spread out, right? But we still have the same shape. We have an interesting thing going on here, though. When we're going to describe the shape of this, it looks like it's roughly symmetric. But we have something else going on here too. If we look at it drawn, even though it's interesting, I'm just drawing this so that we can see that it looks like we have two peaks, right? And it stays as two peaks, right? So because it has these two peaks, we would describe this as bimodal. It stayed that same way, even though we multiplied it by that factor of 3.28, right? It stays bimodal, stays roughly symmetric. That bimodal, by the way, just a little vocabulary term, not super, super important. It is a way of describing the shape. I think that if you were to not point out that it was bimodal, but you did point out that it was roughly symmetric, you'd probably be safe. Right. So that's it. A nice short lesson for you guys today. We'll do some problems in class tomorrow. And then there will be another lesson on the following night. We'll do 2.2. So we're going to knock this chapter out very, very quickly and then move into some more meaty stuff that takes a little more thought. There we go. This is what we did. And you know what? Have a great evening. See you tomorrow. Thank you so much for watching.